Calculus, good morning. Let me see. Everybody have a good weekend? 3 days. Oh, baby. Yesterday was foggy and ugly, and I spent the whole day inside, and now the sun is shining.
Where's the sun shining at? It isn't shining where
Really? Yeah, I guess it is. I do see low fog. I'm in Jacksonville, so I'm a little bit higher than that. Wow. I looked, Justin, at the
Yeah,
Ashland
I think
cans yesterday, and it was amazing up there. I bet it was 15 degrees warmer up there in the sun than it was down in all that fog. Well, let's see. We just mastered our first week of homework. So you did 5.1 and 5.2. Just a note about some things. I mean, there's a couple of questions in there. Philosophically, like I think tests, especially for those of you that are new, should be relatively straightforward. Projects that I give, maybe those will be challenging because you have a little access to me and often time in class to work on them. There's going to be a few random homework assignment questions, individual questions that are pretty tricky. I even sent you an email about one that came up. And sometimes that's because I don't catch them and get rid of them because I really don't overall, I don't really like tricky questions. But there'll be a question or two, either maybe somewhat by accident or maybe on purpose, just to challenge you a little bit. Homework isn't going to, kill you overall. I think your grade for that was at 25% in the syllabus. I forgot. Do I have it written down? I can read it. I don't. So, if you miss a individual question here and there, you can decide, it's not worth it. I'll just let it go. I saw most of you that did the homework assignment were in the high 90s for your homework grade. It's like, you're great. If you miss a question here or there, now that might bug you in the sense that, like, I don't want to miss one. Well, great. Then bug me about it. And let's talk about it. The two tricky questions on that just stand out to me is the one where you were asked, I forgot what section, I know it was 5.2, but you were asked to write out that nasty Riemann sum formula with all the n's in it, like I did in class. If you survived that question, wow, hats off to you. We didn't practice that a ton, and to be good enough at that to get that question right, it's a lot to ask. So you can decide what to do about those individually. But again, feel free to hit me up. I gave you my cell phone number. Text me. We'll have a quick Zoom. I have office hours on my syllabus where what I'm planning on doing is just going into my Zoom room and just sitting there, and you can pop in and ask me questions. But more often than not, your questions are probably going to be Sunday night, in the sense that the ones you really struggle with anyway. You have the weekend to work on them. So don't be afraid to hit me up on Sundays. I mean, some Sundays I'll be out of town, maybe I can't, but if you text me, I'll tell you I can't do it today, or, hey, I'm free, let's do it. I wouldn't have given you my phone, as I said, if I didn't want you to do that. The other one that was weird on there is you're used to finding the area under the curve from, say, and this is what I sent in the email, from 2 to 5. So small number to big number. So you're moving from left to right. And, maybe you get an area of like 12 or something like that. But what if the problem was sort of tricky and said not from 2 to 5, in other words, with 5 on the top of the integral and 2 on the bottom, but what if it was from 5 to 2, like backwards? Well, then you get the same answer, but just negative. And I said that in an email. That's kind of tricky. And maybe sometimes there'll be a question help that can allow you to kind of, oh, okay, I don't know what that means, but at least I got the question right. So that might be available in some questions. And so again, it's kind of up to you. But as I said, overall, it isn't really going to change your grade if you just have a question here and there that you decide, No big deal. So just want to highlight a couple of things to make sure you're rolling on it. Today is the 19th. You owe me the first quiz. So just to make sure you're seeing that, that's part of your grade. This quiz right here. So again, just for those of you that are new, you should be going in here and, I mean, ideally for your sake, you're downloading this quiz. If you have the technology to write on an iPad like I'm doing, great, but print it out and then write on it. Sometimes it's got a figure with it or something, and so it helps just to write on it. But I definitely want you writing in, either electronic pen or, because this is going to be more like the test. These questions, again, should be a little more on the straightforward side, like things I really want you to be able to do on the test. So it gives you a chance to practice, me a chance to tell you what to do. But you also should get 100 on these because you should be checking with other people in the class if you happen to know other people or want to reach out after class. Or again, reach out to me. You're more than welcome to ask questions like, hey, this is what I got for number 7. Is that right? And I'll tell you no if it's not right. So, ask that. Don't just turn it in. Because again, you should be practicing. It doesn't do any good to do a bunch of work and get it wrong. You're just teaching yourself how to do something incorrectly. So check all that stuff. I mean, make sure it's right before you turn it in so that you're, learning something. That's my goal. I mean, this is as I've said before, it's kind of a pain for me to grade all this stuff. So I want to do that, but I want to do it to improve you. So these are due in time on the test, just before the test. They're due in time for me to get them from you, grade them, and get them back to you so that whatever mistakes you are making, if you don't check into it, at least you can go, oh, I see now, and then, get it right on the test, which is where the majority of your grade comes from. So just make sure you're using that to your advantage. So the key, though, in order for me to grade it quickly, because I am giving it to you, so I only have one day to turn this around for 31 of you, which is going to be, 5 hours of grading just for that little period of time. I have to kind of give it late, but make sure it's scanned as a PDF file, and just one PDF file with maybe 4 or 5 pages. And there's a little bit of direction on here about how to do that. And you're going to submit it inside My Open Math. It's going to get lost if it's in email. So I'm going to go into My Open Math and I'm going to see 31 of those PDFs in here, and I'm going to pull them out of there and start grading them and send them right back to you kind of as I grade them. So anyway, I just want to make sure you haven't forgotten about that and you're rolling on it and everything's going.
Doug, I have a quick question about the quiz, actually.
Please go ahead.
On the first problem, we start going over, the left Riemann sums, right Riemann sums, and then we made it to, I was like drawing the graph the whole time, and then it got to the midpoint sum. Can we just take the left and the right and average them like we talked about in class, or should we just draw the whole thing out so we know how to do it?
That's a good question. Let me think about that. The midpoint isn't always going to be the average of the two. I mean, if it's got kind of a curve to it, so you have to plug in the middle point in order to get it. So it isn't, if you take the height of the left side and the height of the right side, the only time the average of those two heights would be the same as the middle is if the connection between those is straight. But if it's actually curved, it isn't going to be the same. So that actually doesn't work.
Yeah, it is curved. Okay, thank you.
That's a great question.
I have a question about the test next week.
Yep.
Are we going to be doing 5.5? Because I remember last term we would have that homework and it'd be due the next week, but would still be on the test because we went over it that week.
Yeah, 5.5 will definitely be on the test. Again, it's due Sunday, but you're crazy if you, I mean, and some of you work, and so I know it's not that simple, but you should be doing that. So 5.5 is next Monday and Tuesday. You should be doing it that night. Just because on a normal day, the very next thing we cover might depend on that knowledge. And so even though it isn't due till Sunday, you should be done with it before then. Otherwise, you're shooting yourself in the foot. I mean, the goal of homework is to practice before the test. And so, and part of the reason I'm throwing a review day in before the test is not so much, hey, let's review. It's just to kind of give you a little bit of time to process. So, we will meet in class and I have a review and we'll go over it. But yeah, ideally be done with that before the test. So yeah, you'll definitely see 5.5 on there. And my review that's posted in, just since we're here, there it is, the blank test review and my handwritten solution. So it's going to look a little bit more like, what your work would look like as opposed to being sort of computer generated and professional looking. It's going to be messy and so forth. So whatever's in that review. I mean, if there are things, basically, I'm going to review it if I think it was important. So in other words, if you're successful with the review, you'll be successful with the test. I'm not going to throw something else in there that's like, oh, that was on page 97. You didn't read that. You know, I'm not going to, I think tests should be relatively straightforward. So what else before we start? Let's see. So, laptop, come to me. I want to, we have sort of a day and a half to do 5.3, and we started it pretty, you know, we got a good chunk into it. So you actually understand what 5.3 is about last time we met. And I want to show you a couple of things, but one of them is it still should bother you, I guess, if I say, if we're taking an equation, wake up machine 2, 4. And we are, let me get a new set of notes here. There we go. Let me share that page. It still should bother you a little bit that this is working, I guess, that this little trick, like we're taking the integral, which is a backwards derivative. We're sort of underivating something. So as a simple kind of an intro, if I take the equation, and let's just keep this super simple and just say it's just a parabola. It doesn't have even an x term. It isn't moved up or down. That's like the simplest non-trivial area under a curve question I could ask you. You have a picture in your mind of what that looks like. And if I say all I have to do to add up all of the heights and the widths of the rectangles. And again, I hope you see that statement right there is really meaningful now, that you see this as a height and that as a width of rectangles. And if I add them all up, again, see that integral sign is like an S for sum. And I'm going to add all of those up. And what we said in the fundamental theorem of calculus is unbelievably, we just have to do the reverse of a derivative. We have to use the power rule and work backwards. And I told you last time the power rule is add 1 to the exponent, so that x to the second becomes x to the third, and then divide by that. Instead of saying divided by 3, I think I'll say times 1/3 this time. And so I get a different equation. I get a cubed equation. And what we're saying is all you have to do to get the area under that curve between any points you want. And so I'm going to say 5 to 2. And notice in the order, 5 is the big number on top and 2 is the small number on the bottom. And it'd be dumb, and only a mathematician would turn those around. But any normal person just says, I want to know the area under that curve between 2 and 5. Then all I have to do is get this brand new equation, and to add up how many rectangles? Well, a billion. Well, not even a billion, more than that, infinitely many rectangles. All I have to do in the fundamental theorem of calculus is in the language of this, you don't write the integral sign again. That's something that's going to bother me. There should not be an integral sign over here because you just did that. You took an integral. It is now done. You have a brand new equation. In a sense, it's coming from the previous equation. We're just going backwards this term. And we're saying all I have to do is evaluate that at 5 and evaluate it at 2 and subtract them, and I get the answer to a billion rectangles added together. I mean, isn't that's crazy that that works, I guess is what I'm saying. So you say, okay, then the answer to that is 1/3 times 5 cubed minus 1/3 times 2 cubed. If I evaluate that answer, then I'm done. What is that? 125 thirds minus 8 thirds, whatever that is. 125 minus 8, what is that? 117 thirds. Is that right? I don't trust myself. I think that's right. Then that's literally the area. You have just added not a billion really skinny rectangles, you've added infinitely many 0 width rectangles. And so the fact that this is an equal sign, not an approximately, it is not an approximately equal to sign, is mind blowing. That should not work, and yet it does. We just touched infinity. Infinitely many 0 width rectangles, and yet it has an answer. And so again, for the sake of the test, you might cheat on your calculator and type in the equation x squared and use that integral cheat button that I showed you on your calculator and sort of make sure I didn't make a math mistake there. That's the fundamental theorem of calculus. You're going in the reverse of a derivative.
Why do we subtract the 1/3 times 5 to the third? Why do we subtract that from the 1/3 times 2 to the third? Why don't we add it? Because we're adding the area. Oh wait, sorry, I got it. It's
You do?
Yeah, because
that is not obvious.
3.
Like why? No, that's actually a really good question. Maybe you answered the question you were asking, but you know, why does that even work? I mean, why would plugging in 5 to some equation tell us anything about area? Like that should bug you. And then why are you subtracting them? That is not obvious. And I do want to show you something quick about that. And I hinted the other day that, and again, this is just interesting. So, you know, why does this even work? Why are you subtracting, and why does plugging a number into some other equation tell you about the area of a different equation? I mean, that should still be a little bit, you know, kind of a huh. Now you don't have to know the answer to that to get all the questions right, so so to speak. But let me show you what I mean. So we said before, why does this work? I said before, the circumference of a circle is 2 times pi times radius. And you already know the area of a circle is pi times radius squared. And the other day I showed you, hey, it's a derivative that connects those. You thought before I showed you that on Thursday or Friday, whatever it was, Thursday, you thought those were just two equations that had nothing to do with each other. And I was telling you, no, actually calculus is relating them. And so in this equation, if I said like, what's C of 5, then that's just telling you the circumference of a circle with radius equal to 5. In other words, the distance around the circle, right? And so, yeah, algebra, awesome. I understand that. But as we understood from the fundamental theorem of calculus, the integral of the C equation actually produced the A equation. Again, can you see that happening? If I take the exponent of R, which is 1, and I add 1 to it, which becomes 2, and then I divide by 2, doesn't it turn into pi times radius squared as an equation? So the integral of the C equation is the area equation. The integral of a length equation is an area equation. Length is a linear distance. Area is a two-dimensional distance. It's a square. And so what do I get if I put 5 into the area equation? If I put 5 into that area equation, of course I get the area of a circle of radius 5, right? But again, what I showed you the other day is, what is area? I mean, reality is area can be thought of as you start with a circle with a radius of 5, and that was the circumference is the distance around it. But what I said is, a cool way to think about what that really is this equation, pi r squared, is saying not just the radius is 5, but the radius is also 4.9, 4.8, 4.7, 4.6. It's like the sum of all the radiuses less than 5. Does that make sense? So when you plug 5 in and you just say, oh, that's a formula somebody gave me and it gave you an area, really what calculus is telling you is that new formula, when you plug 5 in, is actually telling you the sum of all the circumferences less than 5. So let me add that. To this statement of all the circumferences less than 5. Does that make sense? That, my friends, is why this is working up here. When you plug 5 into this new equation up here, what are you getting? Let me see, let's pick a different color. Why does plugging 5 in work? Well, if this is our parabola, and that's 5. When you plug 5 into the 1/3 x cubed equation, what you're actually getting is all of the areas less than 5, just like you are with the circle. Notice r is less than 5 goes from 5 all the way to 0. In other words, it's all the radiuses that are positive and make sense. So the same thing is actually happening with that cubed equation up there. The cubed equation is not the parabola anymore, but it's a brand new equation. And the brand new equation, when you plug 5 in, doesn't just tell you the answer at 5. What it's actually telling you is the area under the curve for all of the x values less than 5.
I have a question.
Go ahead.
So for how you were talking about how all of the radius is less than 5, is
Mhm.
it all less than 5 or does it include 5?
It includes 5.
Okay.
So as a fine point, I should put an equal sign, a less than or equal sign there. You're exactly right. Now, remember though, that the 5 as an area, 5 is sort of infinitely thin. So because it's infinitely thin, does it need to include 5 or not? Well, in terms of area, it doesn't really make a difference. So in a sense, it doesn't make any difference. That's a great question. Let's take a look at 2 then. What's happening when you plug 2 in then? Can you tell me what I'm going to draw here before I even draw it?
All the areas less than 2.
Yeah, all the areas less than 2. So then why would we be subtracting them?
Don't you do it because your width, like your total width, not just the width of your rectangles, but your total width that you're trying to find the area of would be 3. So you need to get rid of the excess area on the left.
Yeah, that's exactly right. See,
Yeah,
this
I was thinking you were trying to isolate it.
Yeah, exactly. Because we really wanted to know the area between 2 and 5. And basically these integral equations will only tell you from 5 to 0. It goes to 0 every single time, just like the area of a circle goes all the way to 0. Like we want the entire area of the circle. We don't want a hole that's missing inside it. If you wanted the area of like a donut or something like that, the only way you could really find it is by finding the outer area and subtracting the inner area. There's no formula for kind of a strip of paper, if you will, that's wrapped around in a circle with a hole in it. Well, that's exactly what we're doing here. That's why the subtraction is part of it. And that's what the integral equation, the cubed equation, tells you about the squared equation. So the fundamental theorem of calculus says, and to find that equation, you just do the same thing you did in 251, except for just in reverse. You don't decrease the power by 1, you increase it by 1. You don't multiply by the coefficient, you divide by the coefficient. So our power rule said, or the reverse of our power rule, that was kind of our last discussion the other day. So anyway, you have some intuition about why you're getting a cubed equation from a squared equation and why you're plugging the n values of that in and why those tell you something, and then even why you're subtracting. That's kind of cool.
Is that why like if you wrote the integral from 5 on the bottom and then 2 on top, that's why it's negative?
That's exactly right. And so if you get them backwards and you go 2 minus 5, that's why you get a negative number, because now you have an area minus an area, but you subtracted the big area from the small area. And so that's why it comes up negative.
Why is it always subtraction though? Like, why couldn't you just add those two? Like if you're looking for the area, it's like the area.
Well, it's entirely based on this picture. Does it make sense if you take these 2 pictures right here and you add those 2 areas? You're sort of adding that little slice right there twice. What we're after in these problems is, let's go black. What we're really after in this question right here is ultimately this area as a picture. We're after that area right there, aren't we? You can't get that except by subtracting them. If you add them, that won't make any sense since we're actually physically after this black area right here. When we say I want the area under the curve from 5 to 2, that's physically what we mean we're trying to figure out.
Okay, that makes sense now.
Yeah, so isn't that interesting? There's some logic as to why you actually subtract it. Again, you don't need to know that to get all the problems right, but it's just kind of cool to understand. And I will tell you, I was a long way in not only into my math education, because I left college with a math degree without understanding why here, but I was also a long way into my teaching career. I taught 17 years in high school, didn't understand it for any of that time. Somebody just told me that you subtract them and plug them in and it works. And I saw that it did. And so I said, oh, okay, great. But I didn't know why. Didn't need to know why. I got all the problems right, but didn't understand it till recently. Did not understand the connection between circumference and area formulas in circles and kind of how this works. So that's just kind of cool to understand.
So this is great and all for this equation, but I feel like the equations we're doing is a lot more complex than just x squared.
Yeah. And
so what
this
happens
course,
when like
yeah, go ahead.
product what happens
Yeah.
when like product rule and stuff get involved?
Exactly. Yeah. I gave you and I said at the start, I gave you the simplest non-trivial equation I could possibly think of. But what if I said, and this is what Eve is saying, what if I said I wanted to know the area under x squared sine of x? We saw last term that the product rule going forward was actually kind of complicated. And so, is there some kind of reverse of the product rule? Yeah, there is. And that's kind of what this course devolves into, is, okay, now that we see the integral will tell you the area under a curve, and that's kind of cool. Okay, well, then let's go find the integral of everything. Let's just make up the craziest equations we can. That's what mathematicians do.
Are we going to have to do like the reverse quotient rule?
That's exactly right. So think about the rules we had last term. We had trig rules. Remember how the integral of secant was, well, that was complicated. And, I don't even have it memorized. I think it was secant tangent. But, we had to look into how to do these things. And the two key ones, well, the three key ones were product rule, quotient rule, and chain rule. And so we got to figure out how to do them backwards now. And and that's what makes this class hard. And frankly, harder than last term. Because last term it was sort of hard to go forward, but isn't even worse to go backwards. One time when I was in college, I decided I was going to try to drive to the store in reverse all the way to the store. It wasn't miles away. I didn't get on the freeway or anything. It was like a block and a half away, and it was late at night, so I wasn't an idiot to all the other drivers and so forth. As you can imagine, harder. Like you can't see, right? You can't see where you're going. You only got a mirror. You got to turn your head around. I made it. It is possible to get there backwards, but it's harder to go backwards than forwards, right? So that's what's going to be hard this term. And so we're going to have a couple of other rules we got to look at. One of them is called integration by parts. That will be the reverse of the product rule. Another one's called substitution as a trick. And so we're just going to sort of practice. How do we handle stuff like that? So we have to reverse the product rule from last term. And, we got to practice that. I got to show you how to do that. Again, what's kind of cool is that question is easy on your calculator, isn't it? You just cheat and ask it what's the area, and it'll tell you an approximate answer to it, and you're done. If you're an engineer, then you say, okay, good, I'm done. This class is over. You showed me the button and we're done. I can now find everything I need to find, and you're not wrong. If you're a mathematician, you say, wow, that's kind of cool. Like, I can't believe we can actually find the integral of x squared sine of x and, be able to figure it out and so forth. That's pretty awesome. And so, yeah, I want to understand that, you might say. So again, that tells you whether you're that's another question that kind of tells you whether you're a true mathematician or not. Now, before we sort of let this course turn into this, I do want to show you something cool. Which I guess I'll call and I actually woke up at 1 o'clock this morning, just for no good reason, just because I'm old. And I got up because I wasn't going back to sleep, and I played around with this to make sure it kind of worked. And then I went back to sleep. What I call this the formulation of an integral. I just want to give you, and as I've told you before, apologetically even, I just want to make sure you kind of understand how integrals arise and why people ask these questions in the first place. And what I'm going to show you is an engineering example, something that I do all the time in construction. And let's see. Dang it, I brought the wrong kind of paper in here. Too late now. Maybe it's not too late. I'm going to check and see. Huh, it isn't too late. It's a good thing I checked. You never know what you'll find out if you're not afraid to ask questions. So what I'm going to do is I'm going to show you just an engineering problem, like something that happens in the real world that is kind of a problem for people. And here we go. 2, 4, 6, 8, 10, 12. Oh, I got lost. 2, 4, 6, 8, 10, 12. There we go. And come on, straighten out. Oh, wow. So this is a retaining wall. What does it mean that it's a retaining wall? That could be a dam where water is behind it. In the case of construction, it's usually dirt that's behind it. So we'll say dirt is over on this side. And can you appreciate that with dirt on this side, and basically the other side of that wall is like your driveway or something like that. So this is what happens all the time on a hill. So if I'm doing construction and somebody says, hey, let's build a driveway right here. Well, then you come in and you chop out a chunk of this hill. So that's gone. But of course, what's going to happen? Well, the dirt's going to want to fall down the hill, right? And so then you come back and you say, okay, well, I don't want that to happen. So I will build a wall right here. And now, come back and erase part of that. Now basically the hill does that, and now you can kind of drive your car right through there. Does that make sense? Probably should write the word car on that since it doesn't look like a car. So this happens all the time. You've driven on roads where this happens. If there's rock over there, then they don't have to build a retaining wall because rock is really strong. They blast it with concrete. But if you do that with dirt, it's going to want to fall over. But of course, what's going to happen to this wall if you just say, good, I'm done, I built that wall? What's going to happen to the wall?
Nothing. It'll stand the test of time.
It will stand the test of time if you do some math.
Is it not just going to fall over into the road?
Yeah, but can you appreciate the wall wants to tip over, if you will? And if you find this interesting at all, and you're going to go into engineering, go do a Google search and search failed retaining wall or something like that. And you'll see places where the dirt's pushed it over and the wall's cracked, or maybe the whole thing completely fell over, etc. And so I want to show you kind of what an engineer has to do. And I actually have to, because I don't have an engineer's stamp. I teach engineering, but I don't have the stamp that says I formally can design this. I have to pay people $1,000, $1,500 to design these kinds of things for houses that I draw. And that's you. Calculus is a necessary class for engineers. And some of you told me last term you're going into engineering, and so you're getting a sneak peek here. But you understand this, perhaps, that if you have a teeter-totter, rather than trying to draw a kid, I'll put an 80-pound kid over here, an 80-pound kid over there. Can a 60-pound kid teeter-totter with an 80-pound kid from basic physics? You don't even have to have physics to know this. How badly does that teeter-totter, if you will, desire to rotate?
I mean, I feel like it'd work pretty well.
Yeah. Do you understand that if, I'll keep this simple, if that 80-pound kid is 6 feet away, that makes a difference that he's 6 feet away. It's not just his weight, it's also how far he is away, because torque is equal to force times distance. And so a force of 80 pounds times a distance of 6 feet is 480 foot-pounds. of torque, or torque is just desire to rotate.
Would you subtract the torque from the other side, the 60 times 6?
That's exactly right. Now, and so basically the kid on the right, in a sense, is causing 480 foot-pounds of desire for it to rotate that way. Now, can a 60-pound kid compete with that? Because it's not just 60 pounds. The answer is yeah. If he sits how far
If
away?
his length was longer. If his length was longer.
Exactly. His length just has to be longer. Now, specifically, what is it? Well, in this case, 60 times 8 feet is also 480. Those two kids would be perfectly balanced now. Do you see the logic in that? It's not just weight, it's also length.
Yeah, but like I'm pretty sure that usually they kind of like jump a little bit instead of just like sitting perfectly still balanced on the teeter-totter.
In this particular case, now in the real world, does the kid weigh 80 pounds? No, he weighs 80.126945, you know, and so you'll never sort of perfectly balance. But the cool thing is these kids would balance, and so you would be able to teeter-totter. Basically, as one kid would push his legs up, and then the 80-pound kid would go down, and then he'd push, and the other kid would go down, and they'd have a good time. But does it make sense if, you know, this kid was actually 600 pounds, then that would just be on the ground, and he would push off, but it would just go up a little and go right back down, and the 80 kid would be stuck up in the air, would never come down. And so as long as you're close, two kids can teeter-totter. And you may have seen on a playground, if probably in playgrounds now they don't have teeter-totters because it's not safe or someone's found a way to get hurt, but they'll have a way to adjust that teeter-totter a little bit one direction or the other, so you can actually get two kids that don't weigh the same weight going. And so this concept of torque, again, what I'm showing you here is the formulation of an integral. What does an integral have to do with designing this retaining wall? Well, it turns out, and I'll just keep this, I'm going to try to go simple and quick. I'm going to use the example that I made up in the middle of the night. Up high, because there's not much dirt up there, we'll say there's 20 pounds per foot. That's what dirt weighs, or what dirt is actually able to push horizontally on a building or on a wall. But down here, we'll say that is actually heavier. And I'm going to say, and I made up some numbers. You won't see why now, but I made up some numbers that are going to make our life easy. Does it make sense that the further you go down, things weigh more? This is the concept behind scuba diving. If you go down in the water, things weigh more. If you take an empty can of Pepsi and you put it at the bottom of the lake, the lake was going to squish it at some point.
Doug?
Yep.
Is the units for that 20 pounds per foot or 20 pounds per foot squared?
Yeah, that can be a little complicated. It can be square feet, and I'm sort of taking the fact that there's a square feet of dirt there, and I'm just saying that every foot I move down, though it's pushing on that wall, will be 20 pounds for vertical foot as I go down. But you're exactly right. It actually is square feet. I'm just trying to keep the unit simple.
I think there would be like leverage towards the top of the wall though, also.
And that's kind of the key, because if you look at this, does it make sense? Two things want to happen. The wall just wants to slide and not tip over, but just slide. So you have to make sure it gets pinned to the ground correctly. And just for your info, that's kind of cool. A real footing will be put under that with that little keyway at the bottom down in the dirt so that it can't push to the left. And so, okay, great. Now it won't push to the left. But then now the second thing is, well, the teeter-totter thing, does it make sense it wants to tip over? But what you need to understand is, do you understand that this is not just one kid on one side of the teeter-totter, but you got a 20-pound kid at the top pushing, and then you got, well, what's the next one? Say 40, and then 60, and then 80. Does it make sense you've got a whole bunch of kids on the teeter-totter pushing over? And ultimately, thanks to calculus, how many kids do you have? Infinitely many. You have infinitely many kids, and the more kids you have, the smaller the weight gets each time. Does that logic make sense? And can you understand
curve
that?
of weight.
Yeah, in terms of weight, you have infinitely many infinitely skinny kids on this teeter-totter if you actually want to get the problem right. And this is not just playing around and saying, hey, I'd like to know the area under x squared for no reason. This is, we've got to know how badly, an engineer's got to know how badly does this wall want to tip over, because this is kind of like a one-sided teeter-totter. Does that make sense? how badly does the dirt want to tip this wall over, which is a torque statement, a force times the distance. And you've got to get that so that then you can say, okay, now what am I going to do as an engineer to keep that from happening? And I guess I won't digress into what engineers do about that. But let's do this. Let's do this with a Riemann sum. Let's first do this with a Riemann. I spelled Riemann wrong. I as before. Riemann sum, where let's say there's only 3 kids on the teeter-totter, n is 3. I took all that trouble to draw this accurately. What I'm trying to do here is teach you calculus deeply enough that you can actually go make money or be an effective engineer. As I said, this class is going to digress into what's the area under x squared sine of x, and nobody really cares about that. You understand that? No one's ever going to come up to you when you leave this class and say, can you find the area under x squared sine of x? They're going to say, can you design a retaining wall that will not tip over here? Because if you can, then I'm going to give you money. If you can tell me the area under x squared sine of x, then I don't care. You're a nerd. Is it cool to find the areas under x squared sine of x? Absolutely. For you math people, I think it's cool. But I think it's even more cool if you give me $1,000 because I know something. So do you see what I'm saying? Although this isn't in the book, I think it's essential to understand where an integral comes from. And that's what the fundamental theorem of calculus is. So let's see if we can do it. So I'm apologizing for sort of not helping you get your homework assignment questions correct just yet. We'll get to that later today. So let's see, if n is 3, would you agree that this 12-foot tall wall, I'm going to divide it into 3 sections. So there, I have done that now. So where, and this is a midpoint Riemann sum, by the way, because what I'm doing is I'm pushing right there. And I'm pushing right there, and I'm pushing right there. And those forces are bigger and bigger and bigger. Do you agree with that? Now, what I said at the top, let's make a little equation over here. I said at the top it was 20, and at the bottom it was 116 pounds per lineal foot. In the span of 12 feet. Well, remember our formula for the width of our rectangles? If I take 116 minus 20 divided by 12, that's 96 divided by 12, which is actually 8. So every foot I go down, and I hate to put units on this because I'm afraid I'm going to confuse you, but it's actually, since 116 and 20 are pounds per foot, and I'm dividing by 12 feet, it's actually 8 pounds per square foot. But basically all this really means is it's a rate of change. If I start at 20 and I go down 1 foot, then it's going to be 28. If I go down another foot, it's going to be 36. You see where I got that?
That this changes linearly, not exponentially.
Say that a little louder, Cody.
It's Vale. Sorry,
Vale.
I'm not sure why my mic isn't quite working right.
I hear you now.
Doesn't that assume that the rate of change is linear?
Yes, and it turns out it is. Like in the case of dirt, it is linear. That's a great observation, Vale. It is linear, as it turns out. Now, would you agree that top third of the wall is not 36 the whole way? This is just an approximation. So let's see, let's go down. 36 plus 8 is 44, plus 8 is 52, plus 8 is 60. So this one is 68. That's 68 pounds per foot. And so let's see, I just went up, what is that? 32. So if I go up another 32, wouldn't this one be at 90? Let's make sure we get to 116. So 90 plus 8 is 98. Uh-oh, I'm afraid I'm wrong. plus 8 is 104. Something's wrong. What did I do wrong? I don't know. Let's see. 20, 28, 36. 2, 3, 4 more 8s is 32. 4 more 8s, 32. Oh, it's 100. It's not 90. I can't do math. 68 plus 32 is 100. But that did model something. Do you do this? I say this all the time in my classes. Are you thinking? Like, do you stop and think if things make sense? And so notice I just found a way to check my work. I wanted to make sure I made it to 116 and I didn't. Therefore, I caught my kind of dumb mistake. I thought 68 plus 32 was 90. You might probably can see why I thought that. So what's the Riemann sum of my force times my distances? Well, I have a force of 36 pounds per foot. But would you agree that that is over a distance of 4 feet? Because that's not just 36 pounds right there. It's 36 pounds over 4 feet. So that's really actually a force collectively. Notice it turns into a force. 36 times 4 is 144. Notice the feet cancel, and so I get 144 pounds. You actually have 144 pounds there pushing on the wall. What distance is it at? Well, it acts right in the middle. It acts right where I drew that arrow. How far is that above this point right here where it's going to tip? This is basically the tipping point down here. How far above that? Remember, it's force times the distance. How far up there is that first arrow that I drew? Somebody blurted out. And I drew this to scale. What is it?
10 feet.
Yeah, it's 2 feet short of the top. So times 10 feet. That's a terrible bracket. Would you agree that's my first torque? So I got one, if you will, 144 pound kid, and he's 10 feet from the rotation point. Plus, I've got a 68 times 4 pound force, and that is 6 feet above. Plus, I've got 100 pounds per foot times 4 feet, but that distance is only 2 feet up. That's a Riemann sum with only 3 forces. If I add that together, 36 times 4 times 10. I'm going to write these down just to give you some time to think about it. And then 68 times 4 times 6. Notice you get more. As you move down, you get less weight. I'm sorry, you get more weight, but you got a smaller distance. And the last one I can do in my head. Is that right? 64 times 8 times 4. And the last one you get 800. I'm bothered. It went up and then it went down. Did I do something wrong? I can't see it if I did.
Didn't you just do middle, bottom, and then you added on the top at the very end of the equation?
I'm surprised that the first number was 1400 and then it went up to 1600, but then it actually went down to 800. I was thinking maybe
No, isn't 800 the top 4 feet?
No, 800 is the bottom.
For the middle number, I got 2,720, not 1632.
68 times 4 times 6.
Oh, I did. Oh, times 6. Okay, let me recalculate.
Shouldn't that be 10? I think it might have just been like a 10 that was like drawn weird or something, because the distance should be the same for all of them, I think. Right?
No, because it's kind of like this back here. In other words, you got this 60-pound
Leverage.
kid, but he's 8 feet away. So these 3 arrows I have here are 10 feet away, 6 feet away, and 2 feet away from this tipping point down here. So I don't think I'm wrong.
I see. Yeah, I think it would go down because that makes sense because there's more leverage at the top, right?
Yeah, there's more leverage at the top, but there's also less weight at the top because you're not as deep in the dirt, if you will. So the point is these torques, these three torques I just got, 1440, 1632, and 800, are a combination of how much weight is pushing and then also what their distance is. And so if I add all those together, I get 3870, 370 foot-pounds of torque. Again, that means desire to rotate. That's how badly that wall wants to tip over. But do you agree that's not the right answer because that's not broken up into enough pieces? Let's do this one more time using Riemann sums, and then we'll skip to an integral. In the interest of, go ahead.
Question. So does the 4 just stay the 4 foot for the force? Does that just stay the same because that's the size of that section?
Yeah, that's exactly right. That 4 is the width of our rectangles, if you will. Again, this is turned sideways. We're used to thinking of it vertically, but that's how wide our rectangles are. It was like 4 times 4 times 4 times 4, just like in our other Riemann sums. Please ask those kind of conceptual questions because that's the only reason we're doing this. Again, I'm not going to put this on a test. This is just a chance for you to actually understand what you're doing. Let's jump it to 6 rectangles. Are we going to get the same answer if we increase our accuracy?
We shouldn't, right? We should get a more accurate answer.
Yeah, we should. My guess is we're not going to get the same answer and it's going to be more accurate.
So where are the rectangles going? Like we're filling this with, we're going to try to fill this with infinite number of rectangles. Where are they being placed right now?
So it's kind of off to the side, if you will, if that makes sense. And the reason I'm showing you this is because these are not areas now, they're torques. The key thing integrals do is they add up infinitely many infinitely small things. And so this is a deeper problem than just area. This is actually adding up a bunch of torques.
Okay.
So we just have 3 kids that were sitting on this teeter-totter, 3 kids, they weighed 36, 68, and 100 pounds, and they were 3 distances away. But we have to increase the number of kids, and when we increase the number of kids, their weights are going to get smaller, but then there's more of them.
So instead of increasing the number of rectangles, we're increasing the number of torques.
Exactly.
Gotcha.
That's exactly right. So we're not actually doing areas here, we're doing torques. So now I'm dividing that wall into 6 parts. So would you agree that that would be here? So there's 6 rectangles, and again, I'm going to push at them from all of these locations, which get progressively longer. And as Vale mentioned earlier, crazy enough, they actually are linear. So in physics, you'll study vectors, or in engineering, you'll study vectors. So the lengths of those lines are actually the weights that we're talking about. So you tell me then, how long, what is the weight on those? Remember, 1 foot was still worth 8 pounds. Every time we went down a foot, the weight got 8 pounds heavier. Does that make sense? That hasn't changed. So if the top was 20, does it make sense this is 28? Plus 8, this is 44. So it's plus 16 every time since I'm going down 2 feet. So this is 60. 76 plus 16 is 92 plus 16 is 108. Did I blow it this time? No, because if you go down 1 more foot, that'd be 8 more, and that's 116, and that was the weight at the bottom. And so I didn't blow it. So What's my sum? My Riemann sum. Riemann is defined as a finite number of rectangles. Does that make sense? I only have 6. I can do that. I can come up with 6. I can get an estimate for this answer. So again, it's a distance of 28, or so I'm sorry, a weight of 28 pounds per foot times how many feet is that part of the wall taking up this time? It's not 4.
2 feet.
2 feet. We have twice as many rectangles, which means they're half as big as they were before. So again, that collectively is the force. Force is pounds, and see the feet cancel, and so you get 50, what is that, 56 pounds there. How far up is that 28 feet? What's its distance?
11 feet.
11 feet. So I'm just going to have 6 of these. So let's see, then I'm going to have 44 also times 2, but that 44 will be 2 feet below the 11, which makes it 9 feet. You agree with that? And then I'm down to 60 also times 2. Every time it's times 2, that's the width of our rectangles. And now it's 2 feet lower than that, so times 7. And then I'm down to 76 also times 2, and 2 feet lower than 7, which is 5. And then 92 also times 2, and then 2 feet lower, which is 3. Let me check my work here. Yeah, isn't that up 3 right there? That's 3 feet up. That's how far away that arrow is at the center of what it's pushing at. And then finally 108 times 2 times 1 foot up. If I add all those up, I'm going to get an answer like I got last time, 3870, except it'll be a little better. To save time, they're all times 2. So I'm going to say 28 times 11 plus 44 times 9 plus 60 times 7 plus 76 times 5 plus 92 times 3 plus 108 times 1. And I got 1888 times 2. I got 3776.
How could we write that more compacted?
Yeah, that's a great question, Alicia. And that's exactly why Riemann sums exist. Does it make sense that if you were able to rewrite this as something with a bunch of ends here, like some formula? Because you're quickly realizing, I hope, that now we need to jump to 12 rectangles and then 24 and then 48. But it's like, man, this is going to get confusing. But there's definitely a pattern. I mean, if you look at these numbers, this 28 right here was the start, and then it went 16, and then it went 16, and then it went 16. And notice the foots started at 11, and then it went 9, and then it went 7. Does it make sense? That's patternistic. And so I could write some formulas with ends in it. And you'd be able to kind of write down a pattern. And that's why some mathematicians would say it's really worth practicing. That hard question that I referenced on the assignment is, can you actually write a formula for n there? Turns out, this is the calculator program you wrote, except for we're doing a midpoint Riemann sum here. Does that make sense? This is a midpoint Riemann sum. Why is it a midpoint? Because we chose that to be in the middle of its rectangle. Our rectangles were 2 feet wide here, and we put that height in the middle. We didn't choose the top and say it's 20 feet. We didn't choose the bottom, which would be 36. We chose the middle. And if we're estimating, isn't that the best place to choose?
Yeah.
I think we're approaching like 3,500 pounds is going to be where the wall needs to be at.
Yeah, so let's see. Notice it was 3870, and then it went down to 3776. And so it does sort of imply that the answer is actually going down. And so the question is, what is the limit? And so I think that was Felix that said that. Does it make sense? The limit is kind of the key question here, because the right answer to this question is really important. And do you understand, in the real world, there is infinitely many, the right answer to this is infinitely many slices that are infinitely light. Like, that's the right answer. There are infinitely many skinny kids on this teeter-totter, so to speak. Like we're just getting approximations, but this is, does the house tip over? Like you can't afford to not get this right. So I'm going to show you something really quickly. I was amazed how easy this was to fix at 1 o'clock in the morning. So I wrote a left Riemann sum program for you the other day. And I think even though this is a virtual calculator, that I think it's saved on here. So let's go see if it did. So if I say, yeah, it's in there. Here's all I have to do to fix this. I'm gonna look at my calculator, make sure I don't screw this up since I only did it once in the middle of the night. Where do we start for our first length? Remember with a left Riemann sum, we actually started right in the middle of this. And so, and A was kind of where we started, right? We went from A to B, but I don't want to start at the left-hand endpoint. I want to move to the center. So does it make sense? You have to start from A, but then move halfway across the rectangle. So see if this makes sense to you. If I take A and I add to it half of whatever the width is, doesn't that put me in the middle of the rectangle? See the logic in that? Please chime in. I see people chatting and stuff, but I'm not taking the time to go look over at that. So if you feel like there's something you want to say that, you know, I need to respond to, say it out loud. If you're just talking to other people in the class, then awesome. I'm going to store that back in A. So now that's going to put me in the middle of the rectangles, not at the left. And then the only other thing I have to do is, this time I wasn't just taking the height. Remember Y1 was the height of the rectangle. And I was plugging in that A value, which I've now just, but I was taking that height, but then I was also multiplying it by the height. So I just have to insert a multiplied by A here. So this Y1 times A, or I'm sorry, the Y1 of A is telling me kind of my 28 pounds. But then I'm actually multiplying by how tall that was. Does it make sense? This is my torque. And then again, I'm waiting till the very end, like I did just a second ago, to multiply by my W. Like this is all I need. So I just fixed this program and it's going to do this work for us now. The only problem is, second quit, what equation do I put here? Like we haven't had any equation. Let me quickly go back and show you that now. And this is basically what Alicia was saying is like, you know, what's the pattern? What's the pattern to these numbers right here? That's one of the patterns we could look at. What's that pattern? Well, really that line right there, I'm just going to give you the equation in the interest of time. That line or those numbers can be found using this equation. Let's see, those are forces.
I don't know if it's just my screen, but I can't see your work right now.
Yeah, I can't either.
I can't see anything either.
Thank you. It's my fault. I didn't mirror my screen. So thanks for chiming in. Totally my fault. So we're trying to find a pattern. Well, here it is. Y equals, if you start at the bottom, and what I'm going to do is say this is 0, like this is my graph. My graph is right there. If I say Y starts at 116 and you lose 8 pounds for every foot, I just want you to notice that that actually works. Actually, I'm going to change that X to an H so that you understand that we're talking about height here. So that distance up is H. So that 28 up there, isn't it a height of 11? So if you plug 11 into this, 116 116 minus 8 times 11. Hey, I get 28. That's effectively what Alicia was getting at is, is there some pattern to this, some formula? There's my equation right there. That's going to give me my 28s and my 44s and my 60s. Do you understand that? So that's the equation, 116 minus 8h. That's the equation I got to have in my calculator. Let's go try it. And let's see if we can get this to work. Share screen. So 116 minus 8 times, and I have to say x here, I can't say h, which is confusing because it seems like it's horizontal. Second quit. So let's try this. So I want to execute this Riemann sum program, and I hope this works. So I'm going from 0 to 12. Do you agree with that? That's how tall my wall is. My heights are from 0 to 12. And last it asked, how many rectangles do you want? Well, we started with 3. We got 3870 in class, which now that I just did this, I think we got it wrong in class. I think I just wrote it down wrong. Yeah, I did. I typed in my calculator 1630, not 1632. So, and none of you told me that you got, and some of you knew that probably, or you probably assumed, hey, he can add, he's not going to screw it up. We'll get the next one right. Let's do it again. Enter. This time, let's go from 0 to 12. But the only thing we're going to change is we want to have 6 rectangles. That's the answer we got, 3776. Again, isn't it cool that you can make a program that will do this for you? Let's do it again. What we didn't do in class, which is let's jump to 12 rectangles. And I think it was Felix that posited that maybe this is on its way to 3,500. Let's see if that's true. Let's jump to 12 rectangles. 3752. Let's jump to 24 rectangles. 3746. Notice it's reaching a limit. It's approaching something. Notice it only changed by 6 that time. Where do you think it's going to? I'm going to go to 48 rectangles. Last time it was 3746. This time notice it's taken a little while. 48 rectangles is a lot to add. 3744, you're probably thinking it's not going to make it to 3,500 now. What do you think it's going to go to?
Yeah,
3740.
I did 100 and it's at 3744.1152.
Yeah, I'm going to jump to 96 rectangles now. It's going to take twice as long as the last one. I think that was, I didn't look down to see whose screen was highlighted, but I think that was Cheyenne that said that. Notice it went to 3744.125. All right, let's go back and use the fundamental theorem of calculus and actually get the answer exactly correct using calculus, which is what you would be doing if you were an engineer. We need the right answer and we need to get it quickly. So I'm sharing my screen this time. So just for the sake of the notes, I think for the sake of the notes, I'll go back and write those in, n equals 12, n equals, and so forth. But I'll just go back to the fundamental theorem of calculus, where we say infinitely many rectangles. And so what am I going to do? I'm going to say, let's add them all up from 12 to 0. Now go back and look at this. What was our formulation? We had to take the 28. I'm looking at this right here. We had to take 28 and then multiply it by our 2. The 28 came from 116 minus 8 times height, right? That was effectively our 28 in the previous problem. And then we multiplied by 2. But what's going to happen if we keep going? 2 was how tall the rectangle is. How tall is the rectangle going to be? It's not going to be 2 now. What is it going to be?
It'll be dx.
Nice job. It is a tiny amount of height, infinitely small. And I said h because we're talking about h's here, not x, but that's Alicia is exactly right. Isn't that height of each rectangle going to get really tiny? When you say dh, that means h, but an infinitely small amount of h. In other words, that's actually on its way to 0. That's effectively where our 2 came from. That was the size of a rectangle. So collectively, that was our force. And then what did we multiply by? What was that last number? Our D, our 11. What was our 11? Just drawing a rough scale drawing here, but really, that's your actual height. Like, how tall are you at? Where are you at? That's your height. There's our equation. That's going to give us the perfect right answer. It looked to me like it was on the way to 3744. You can do that right now because you understand the fundamental theorem of calculus. Let's see if we can get it to work. So if I distribute the h into this, then wouldn't I have, notice I haven't taken an integral yet. That's why I still have the integral sign. Wouldn't I have 116h minus 8h squared? So the fundamental theorem of calculus says, let's take the integral of that. What do I do to take the integral of 116h?
You do the reverse.
I take h to the 1 and I make it h to the 2. I add 1 to the exponent. And then what do I do to that exponent?
Put it over 2.
Over 2. Same thing with 8. 8 becomes 8h not squared, but I add 1 to that, it becomes 3, divide by 3. What have I done now? I have taken the integral. I made a brand new equation. I took a squared equation, now it's a cubed equation. What do I do to evaluate it? I stick in 12 and I stick in 0. Why am I extremely happy about that 0 right there?
Because you don't have to subtract anything?
Yeah, because when you plug in 0, you're going to get 0. So all I really have to do is plug 12 in this case. Do it on your calculator. Plug 12 into that. What do you get?
$3,744.
Are we surprised by that? Isn't that the limit we saw it approaching just a second ago? When we did 97 rectangles, it was 3744.125. And I think Cheyenne, I think that was Cheyenne that said she did it with 400 rectangles and it was even closer to 3744. It was approaching the limit.
I am surprised it came out even.
Yeah, isn't that cool? It came out.
Carefully picked numbers.
Isn't that crazy? The carefully picked numbers were actually just to make sure all of our subdivisions were whole numbers. I didn't want to have, I had 28. I didn't get 28.675. I never had any decimals there. But basically what I'm saying is up to this point, these were approximations of the torque. Sort of, the torque is, the actual torque is approximately equal to that. So, you know, is that good enough? If you did this with 6 rectangles, is that a good enough number? Well, that's not terribly far off 3744. And frankly, it was a little too big. Therefore, you know, at least you designed it for the worst case scenario.
Yeah, it's always good to over-engineer.
Always good to over-engineer. So this is actually perfect now. Do you understand that? That's really cool. Again, why did I show you this? As I said at the start, this is the formulation of an integral. It's this type of question that caused calculus to get invented in the first place. It's exactly what Alicia said, which is there some kind of a pattern to this? Is there some way to write a formula for this so that we don't have to just keep guessing and having more rectangles and adding them and so forth? That's what's so amazing about calculus. The fundamental theorem of calculus says, yeah, if you can write out an equation for this and then do the reverse of a derivative, then you can just plug 12 in and you got the perfect answer. You just added infinitely many, infinitely small torques. Infinitely many, infinitely skinny kids. That's how badly that wall wants to tip over. Now, as an engineer, then you say, okay, now what am I going to do to keep that from happening? In the case of engineering, what you do is you tie stuff to the wall Like you put a piece of metal that goes back into the dirt so that that plate has to pull through the dirt and then it won't tip over. So what we just calculated is what's called the tipping moment. No, what is that called? It doesn't matter. So there's a tipping moment or a tipping torque, and then there's it's overturning. That's what it was. Overturning torque. There's an overturning torque, and then there's a resisting torque. What do we have to do to resist that? So we might put plates of steel back into the dirt and so forth. So, you know, $100,000 might be spent building this retaining wall just for a house. And so we really got to guarantee it isn't going to tip over, because then you just got to tear it all out and start over.
Couldn't you do the teeter-totter effect and just dig the wall so deep that the exposed was shorter than the depth?
Mm-hmm. Yeah, there's all kinds of ways to fix this, but they cost money. That's kind of the problem. And so we calculated the desire this thing has to tip over. And so you have all kinds of ways to fix that. What Cody just said is exactly right, which is, couldn't you just dig way down and pour that wall way underground so that the portion that's underground won't tip, and then the top just wants to kind of bend out? Yep, totally a solution. Now, that last question right here where I said, you know, what is that integral right there? That's a problem. That's the kind of problems that are in your assignment. You don't have to make it yourself. They just say, here's an integral. Can you find that area? And this is easy because it's the reverse. But let's play around with some other ones now in terms of just kind of trying to get your homework assignment correct. And I'll spend, you know, some time, a little bit of time today. We're almost out of time. But some more time next time, kind of help making sure you can get your homework assignment questions right. But let me give you an example of some that you should know right now. And you might have to look at your note sheet from last term, but why do you actually know this one right now? What's the integral of cosine?
Because the derivative of sine is cosine.
Because the derivative of sine is cosine going forward, then wouldn't the integral of cosine be the sine?
Plus c.
Nice job. Technically, plus a constant, because if that was the sine of x plus 7 and you took the derivative of sine, you'd get cosine, and you took the derivative of 7, it'd be gone. Technically, there could even be a constant there when you're working backwards. So that's a very good point. That looks like an infinity sign, so I better work on my handwriting a little bit. You see what I mean? Like you already know that. You're not used to going backwards, but you already know that. That's the fundamental theorem of calculus. So if I wanted to know the area under a cosine curve, then you plug numbers into the sine curve. That's what that's saying. That's interesting. Almost hard to believe that works, right? Well, what else do you know then? What other integrals do you know? If you look at your cheat sheet, if you will, from last term, not all of you have that cheat sheet. Maybe I need to post that.
Where did the C come from?
I made it last term as like all the derivatives that you know. But the trig ones are the ones I'm thinking about right now. What was the derivative of tangent? Does anybody have it memorized or have a sheet? What's the derivative of tangent?
Cotangent.
Not cotangent.
Secant squared.
Secant squared. The derivative of tangent is secant squared. So the fundamental theorem of calculus says, oh, well, if that's true, then what's the integral of secant squared? Tangent. That's the fundamental theorem of calculus. So there's some you know right now. So if you want to know the area under the secant squared curve, then you plug numbers into the tangent curve. Really? Yeah. That's the idea. Let's see, what other weird ones do we have? What about e to the x? What's the derivative of e to the x?
E to the x.
E to the x. So then the integral of e to the x would also be e to the x. Notice I was a little lazy that last time. I didn't write the little dx in there. Notice you actually don't do anything with the dx. It's there because you need to think this is the height of my rectangle and this is the width of my rectangle. But you're really just paying attention to the cosine. So out of laziness, sometimes I won't write that. I'll try not to because I'm supposed to be demonstrating good behavior. And as Vale pointed out impressively, these could have a constant stuck on the end of them. Do you see why?
I I don't see why. I was gonna ask if you could say that again. Sorry.
Thank you. So if I asked you to take the derivative of the tangent of x plus 8, the derivative of tangent is secant squared, but what's the derivative of 8? Nothing.
Okay, that makes
You
sense.
see how that works? So there could actually, you sort of don't know. There's actually all kinds of answers. Now, if you think about it, that should bother you. Like, isn't that going to screw up the area if you add 8 to it? But remember, you're plugging 2 numbers in. So if I said I wanted to know the area under secant from, say, 7 to 3, then wouldn't you be taking the tangent of 7 plus 8 minus the tangent of 3 plus 8? What happens to the 8s? They just subtract out. 8's in both of them. So you have 8 minus 8, they go away. So it actually doesn't make any difference.
So couldn't you have this constant at literal, like any integral in?
Yep. And if you keep going in math, if you are going to be an engineer and you have to take some of the advanced classes we teach, like differential equations and so forth, there's times when that constant actually makes a difference and you can't just ignore it. In our case, because we're doing what mathematicians call definite integrals, meaning we're actually evaluating this from 7 to 3, we're going to get a numerical answer. Then you can just treat the constant as 0. Since it makes no difference anyway, then you just ignore it. For definite integrals, you just get to ignore it. So I need to shut up here, but let me just quickly share the sheet that I had from last term that I'll post it. I'll post it in my open math so you can get to it. Let me go into calculus and into math 251 and into tests and calculus notes. So this is, in a sense, everything you left calculus knowing. The only things that are helpful on here, well, are these trig functions. Do you see how we're going backwards? Like this term, I could say, what's the integral of secant tangent? And you'd say, apparently it's secant. You see what I'm saying? What's the integral of 1 over x based on this sheet? The integral of 1 over x is natural log of x, because the derivative of natural log of x is 1 over x. That's the fundamental theorem of calculus. To find the area, you just do the reverse of the derivative. So there's a few that you know right now, even weird ones that you barely studied. What's the integral of 1 over 1 plus x squared? Apparently it's inverse tangent or arctangent. So you know some of these.
So I'm wondering, a lot of them have like a bunch of really complicated multiplication and, you know, divisions and stuff. And I'm wondering if any of them get kind of some information lost between going back between like derivative and integral, where like you can't tell for sure what the one answer is.
Super good question. It turns out you can't. It takes crazy creativity to find some integrals, and there are some that in a sense no one's ever figured out or are impossible. Now you can do them numerically, like you can get on your graphing calculator and sort of cheat and ask it the area and it'll give you an approximation, but you can't always come up with a formula, a literal formula, like you can in these easy examples. What's the integral of 1 over x? It's natural log of x. I know the answer. It's perfect. It's easy. But if I change that to 1 over x squared, well, now all of a sudden we're in trouble. And we're going to have to think. And so this takes a gigantic amount of creativity to basically solve all problems when we start messing with this. This is all you need to know right now, though, is just simple stuff. And primarily it's the power rule, which is what we did with tipping over the wall. It's a squared equation. The reverse of the power rule is not hard at all. And I wrote that in last week's notes. And so do you see what I'm getting at, though? Do you see the concept? And so now what does this class reduce to? It reduces to, let's find the integral of other stuff that isn't so obvious. I see here that the integral of cosine is sine, but what's the integral of tangent? Notice tangent's not over here. There's nothing that says tangent here. What's the integral of tangent? I don't know. Guess I'll have to try to figure that out. Like that's what this class reduces to. Just like last term, after 1 week of introductory concept as to what a derivative is, we said, okay, let's go try to take the derivative of everything. And we ended up with the product rule and the quotient rule and the chain rule and all these different tricks and that mathematicians have come up with. And now we got to do the same thing for integrals. Let's go take the integral of everything. And we can check our work because of the cheat button on the calculator, but let's go take the integral of everything. And we're going to need some tricks. One will be called integration by parts. Another will be called substitution. Those are the two main tricks. And sometimes those substitutions take a gigantic amount of creativity. You can appreciate that if I said, what's the integral of secant tangent, without this little chart here, you'd think, uh-oh, that looks like the product rule. And so going backwards, that's going to be really hard. And so, you know, what would I do to get that? I don't know. I'm going to think about that. Or secant squared. Secant squared is secant times secant. You know, what's the integral of that? Doesn't that look like chain rule? Isn't there secant and then also squared? Isn't that like chain rule? So it's like, oh no, I got to do the reverse of chain rule. If it wasn't for this little chart here, I wouldn't know the answer to that. If I said, what's the integral of cotangent squared? You realize cotangent squared isn't over here. So we think, uh-oh, I'm going to have the reverse of the chain rule somehow to be able to get the answer to that. And so that's kind of where this class is going from here. So your assignment now, and you probably could do a decent chunk of it, although I'll tell you the first 3 questions are more conceptual and weird on your My Open Math assignment in 5.3. But the last, I don't know, 7 or 8, you can do them right now based on what I've showed you, because we're only going to be looking at kind of the easy ones, because all we're saying is, hey, all I got to do is underivative and plug some numbers in, and then I can know what the area is. That's all you got to know for 5.3. So I'm going to spend tomorrow at the start just kind of prepping you specifically to get the weirder questions right in 5.3. You will get the most out of tomorrow's discussion if you actually try the 5.3 assignment before tomorrow and like get stuck on the ones that look weird. And maybe that's our discussion around tomorrow. So we'll probably spend 20 minutes tomorrow just talking about some of the details of how to, you know, get some of those weirder questions right. And then we'll go on to 5.4, which is, and we'll get into that tomorrow, which is, it's titled Working with Integrals. I don't really remember what that means. Cool. Anything else for the good of the cause before we go? All right, get yourselves out of here. Stay after if you want to ask me any questions as usual. Otherwise, I'll see you then.
Thank you.
I've got some questions, but they're pretty far off any kind of topic that we're discussing. So unless there's like literally nothing else anyone's asking, then we can wait.
Thanks, Felix. That's a great way to approach that. Anybody have some practical questions based on what we did? Felix is a deep thinker, so he's got complex questions, curiosity-related questions to ask.
I was gonna say that the other day, like when we wrote the program in our calculator and stuff, I was doing the very last question on 5.1, and it involved like 15 things being summed together. And basically, they were trying to show in the video like some way of doing it with like factoring and stuff like that. And I was like, well, I don't want to do that. So I wrote a C++ program to do the problem for me.
Mm-hmm.
It was like, oh,
I commend you for that.
I can still do
that's
that.
A better approach. Yeah. Good for you.
Yeah, it was just like the running the program on the calculator like inspired me. I'm like, oh yeah, I did take 3 terms of that. I might as well just see if I can brush off the
Whole point is to be
webs
able
and
to
make
use
it
it for
happen.
something, so, yeah. I love it. Good for you.
I'm just curious about the questions now.
Yeah, sure. Go ahead, Felix. Looks like you're up.
Oh, this is I don't know where this thought came from, but I was wondering if there's really anything that I guess mathematically distinguishes whole numbers from non-whole numbers.
That's a really good question, actually.
I don't know. Someone was just talking about like whole numbers or something. I don't know. It just came up.
The answer is actually no. Like, is there anything special about landing on a whole number? I mean, it's kind of funny because I've taught math for elementary teachers, which kind of addresses these strange questions, or I probably wouldn't have an answer for that, Felix. But really if you sort of look at the evolution of counting, it really started out with, and this is really kind of cool, but if you look at my hand, you say that dude has 5 fingers. And so the number 5 is telling you how many fingers you have. If it wasn't for numbers, you'd have to say, how many fingers do you have? And I'd have to say finger, 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 finger. You see what I'm saying? Or if you went to the drive-through at Taco Bell and you're like, what would you like? And you said taco, 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 taco.
Yeah.
If it wasn't for a number. And so whole numbers are an interesting subset because a lot of times, and those are called discrete numbers or, well, whole numbers. If I say how many people in this class, the answer to that is a whole number. If I say how many fingers do I have, is how many fingers I have a whole number?
Yeah.
Unless one's chopped off partially, like you can have 4.5 fingers. And so some things divide up. If I say, what's the temperature outside, is that a whole number?
Probably not.
It isn't, because it'll be like 46.21895 degrees. And so there are different ways of quantifying things where the answer is a whole number. How many cats do I have in my house? That's a whole number. You don't have a choice. But there's all kinds of things, numerical questions that you ask where the number isn't going to show up as a whole number. And then those non-whole numbers break down into classes, because some of them are fractional. Like if you said, let's see, if you said, how many pizzas did your family eat? The answer might be 2 and 7/16, meaning they ate 2 whole pizzas and then 7 out of the remaining 16 pieces. So the answer is fractional. As a decimal, that turns into either a repeating or a terminating decimal. But if I say, what's the temperature? That is not a repeating or a terminating decimal. It's just a decimal that goes on forever with no pattern. Therefore, you can't write it as a fraction. And so with respect to thinking of numbers evolutionary, you can imagine, 2 farmers or 2 cavemen or whatever saying, how many cave do you have? And they're going to say 2 cave, 3 cave. Like whole numbers are going to sort of get invented first. And it's only as, if you will, technology increases, where you say things like, are you done plowing your field? And then you say, well, no. How much do you have done? You sort of don't have a choice but to say 3/4, 7/8. I'm 7/8 done. You can see how, the need for a fraction would have come up to invent. And it's interesting because, that's what we're working with here. We're saying you have a fraction of the weight at a fraction of the distance. Have I answered your question? I'm not sure.
Yeah.
Certainly.
I guess the one other thing that I was kind of thinking of after I started thinking of that was there are certain like irrational numbers that can't be expressed as a fraction between 2 whole numbers.
Correct.
Is that only a product of like our base 10 numbering system, or are there like theoretically a numbering system where those are rational and we can work with those rationally?
That's a great question too. I want to say no, but I'm not really sure that I can say that. Our system is base 10, most likely because we have 10 fingers. And again, it's super interesting to look at the different numbering systems that different cultures have created, the symbols they use to stand for them. And ours is a place value system. So if I say I have the number 25, that's really 2 numbers, 2 and 5. But the place that they're located tells you something about the meaning of it. So 25 is 2 10s and 5 more. 5 is in the 1's place, 2 is in the 10's place, so 2 10s. But the Babylonians used the same thing, but they had 60s. So if they had the number 25, it'd be 2 60s plus 5 more. So they would have been thinking of 25 for them would have been actually 2 60s, which you would think of as 120 and 5 more. So that'd be 125. How many sheep do you have? 2 5. And for them, it would be like a whole bunch of sheep, 125. For you, it'd be, 25 sheep. So they had a base 60 system, and that had to do with the solar solar calendar and so forth, why they chose to regroup at 60. Romans don't have a place value system at all. Their system is entirely, who cares where it is? Well, that's not totally true. I guess if you have x1, that's 11, and 1x, that's 9. So maybe place value is a part of that system. So the simplest way to talk about irrational numbers, numbers that aren't fractionable, is to think of the hypotenuse of a triangle, a right triangle that lengths are 1 and 2. So you'd say, oh, Pythagorean theorem, 1 and 2. I'll square 1, I'll square 2. That's 1 plus 4, that's 5. So that distance over there is the square root of 5. Maybe, and I'm just thinking out loud because I actually don't totally know the answer to your question. If you say, no, I'm going to live in an irrational world, and I'm just going to call that 5. 5 in crazy land, 5 in Pythagorean theorem land. And so you sort of leave the square root off and you say, I'm going to call it 5 in this land. And that would probably work, except for then when you said, how many sheep do you have? Now you can't just say I have 2 sheep, because really when you say 2, you mean the square root of 2, which means you have 1.414 sheep, and that's not really what you mean. And so I don't know if that helps, but that's kind of the problem there, if you will.
Yeah, well, it definitely gives me a lot of things to start thinking about and looking up maybe.
Yeah, it's fascinating how complex just regular old numbers can be if you choose to really dive into it. So cool.
All right, thank you. I'm probably going to head out soon.
Yep. See you later. Any other thoughts, those of you that are left?
Question just popped in, and I can do it. I'm guessing you went over it on Thursday. I haven't had a chance to look at that lecture yet, but the antiderivative stuff.
Mm-hmm.
That's sort of like, I see that it works, but it's sort of like magic to me.
Yes.
I don't know where it came from.
Yeah, and really,
if you went over it Thursday, that makes sense. I can just go watch the lecture.
Really, we did, but in reality, that's kind of the only good answer to that is kind of what I shared at the start of class today. I'm going to reshare that right now, reshare my screen right now. And I might not be answering your question. I might not be answering the question you're actually asking, but really what we did here is we took the antiderivative of x squared and we got 1/3 x cubed. So we took the antiderivative, derivative backwards. We got x cubed. And then we said, okay, cool. Now, if you want to know the area under the original equation x squared, then you just have to put in 5 and 2, since that's the definition of where we said we wanted to find the area between. That's a choice that's totally up to you. We plug those into the antiderivative, and it actually tells us the area under the non-derivative, the x squared equation. And so that business that I said about the circles circumference and area, the fact that if you take the antiderivative of 2 pi r, you get pi r squared. And so the equation pi r squared actually tells you the sum of the areas under the circumference equation, the sum of the circumferences. Well, the sum of the circumferences is an area. That's why that works. And so when you plug a number into the AR squared equation, you're actually getting the circumferences from 5 all the way to 0 every single time, which is why it worked in that red equation up there. So we said, hey, if we put 5 into that cubed equation, that's going to give us all of these areas from 5 to 0 automatically in the
all
original
those like
equation.
little lines. Yeah. Okay.
Yeah. So it's like the sum of all the heights. Because
Okay,
this
that
x
makes-
cubed equation, we're getting the sum of all these heights. And so it's just really, it's amazing. It's like, wow, that works. That's really cool.
That clears it up, but then I guess that kind of leads to how the hell did they do that with the circumference and the area? I guess it'll just keep going, or is there like a finite? This is why they did the antiderivative.
I'd say I still have things to learn, but let me just highlight one other thing. If you take a sphere, the surface area of a sphere is 4 pi r squared. Can you tell me from today what the antiderivative of that is? Just talk out loud. Don't just tell me the answer, like talk out loud as to how you're going to get it.
R cubed divided by 2, so it'd be 2 pi r. cubed.
Not divided by 2, divided by 3. You divide by
Divided
the
by
number
3, yeah.
after you add to it. So you add 1 to the 2 to get 3, which you correctly did, and then you divide by the 3.
So you divide
So-
by the new. Okay.
So you get 4 pi r cubed divided by 3. What is that right there? That tells you that's the sum. That new formula would be the sum of all the surface areas. All the surface areas. In other words, it's like the surface area of this sphere, and then you move in a little bit in the surface area of that sphere. You move in a little bit, surface area of that sphere, move in a little bit, surface area of that sphere. Hey, if I fill that whole thing up with surface areas, I'm actually getting the volume, and that's exactly what that equation is telling you.
Okay, that's crazy.
It's unbelievably crazy.
That's really cool.
And I don't know the answer, and I'm also baffled by, I mean, it's one thing for me to kind of explain to you something that somebody explained to me, but there was a person that figured this out first, and I'm really curious as to how they figured that out or where that idea came from. That just seems like a flash of brilliance that is well beyond the way my brain works.
Me as well. Yeah.
And as I said, I graduated with a math degree and taught math for a long time, and I didn't know that. Like, nobody showed it to me, and I'm fairly convinced most people don't know. Like, that's the reason. Like, I wasn't told because they don't know. They don't understand it, kind of this deeply. They were just told that if you take the antiderivative and plug the two numbers in, it'll tell you the volume. And because the teacher said that's true, then the student did it. And when they turned it in, they got it right. And so for the most part, when I'm out in the world and I say, they say, what do you do for a living? I say, teach math. And what do you teach this term? I'm teaching calculus. And then they'll say to me I've never heard anybody say anything else. They'll say, I took calculus. I don't remember any of it, which makes sense because it's hard. But that's why I think
It
it's
just also
important
makes it super uninteresting, in my
Exactly.
opinion, if you go for that way.
My attitude is, if that's true, then you should have never taken it or never had to take it. Like,
Yeah.
does a dentist who has to take calculus, does a dentist need calculus to do his job? No. He probably had to take it because this principle of adding up infinitely many, infinitely small things shows up in science classes, and therefore take it. And so, in engineering, for instance, I showed you today the formulation of how to figure out if a wall is going to tip over, and it's actually a calculus concept theoretically. But the problem is when we teach calculus, we don't ever teach anybody to think. We just tell them how to take the integral of x squared sine of x, which nobody cares about. And
Yeah,
so-
that's why I love the projects in here, in the last class at least.
Yeah,
And probably this class too. It really challenged, like the math part of it was more homework, quizzes, tests, but then the thinking part was always the projects.
Yeah, you're exactly right. And I'm apologetic about that because they're kind of painful. The first one I'm going to show you is probably the neatest. It's about kayak buoyancy, and it's probably the single neatest math problem I've ever thought up on myself. I thought it by myself. And I was just asking the question in my kayak, if I'm sitting in my kayak, what I felt was if I tip over a certain distance, then it'll just kind of right me on its own. Or like a ship in the ocean, like it tips a little bit because of the wind or the waves, and then it wants to right itself. But if you tip far enough, then you actually tip over. And so it's like, where's that line? Where's that dividing line? How do you figure out where the boat will actually tip over? And you can appreciate as a engineer of ships and so forth, like that'd be good to understand. And
Yeah, that kind of reminds me of the physics friction one. Where's the point of friction where it just the static goes to
exactly. Yeah.
Yeah.
Like you put this calculator on a slope and it sits there because of friction, but at some point when you lift it enough, then it starts to slide off. So we're like, why is that? And so I teach that in my engineering classes. Neat stuff.
There it is. I'm excited for it.
Yeah, love it.
Alrighty.
See you
Till tomorrow.
tomorrow, my friend. Bye-bye.
Thank you.